Mike, are you out there? Hopefully you're still with us.
Still here.
All right, I am going to make you the presenter so that you can take over the screen.
There. Can you see my screen, Rob?
We can see your screen, yeah, so please take it away.
All right, thanks, guys. So what we're going to do is we're going to go through a sample upgrade, and to build on the point that Rob talked about, we already upgraded the manager, so we're simply going to upgrade the storage pool or the slice stores that are a part of this smaller system. So as you can see, I'm actually in the manager user interface right now, and you can see that we have one manager, one accessor, and 9 slice stores. So I'm going to go to the maintenance area of our UI, and I'm going to go into the upgrade section. And you can see it's kind of through a wizard or step kind of process. You initially deploy a file, which is here. I've already done that part of it. Then you upgrade the manager, which is also already done. And then you come down and do the rest of the devices. And you can either do them one at a time using the upgrade buttons, or you can do an entire storage pool at a time using that bigger one. What I'm going to do in the meantime is we're going to kick off a little bit of file operations just using a simple bash script that, let's see if I timed out here. Oh, I timed out, 1 second.
So the first step that Mike started describing there is on my chart where I said, you put the image that represents the upgrade onto the manager appliance, which is then going to orchestrate the distribution of that upgrade across the rest of the dsNet.
All right, there we go. Is that text big enough for you guys to see it for the most part?
For the most part.
For the most part, it sounds like.
All right. So all we're doing is running a basic bash script that's going to pretty much continually use a curl command to write a picture over and over and over again to the dsNet as a way of showing that we can continually do I/O on the system. So I'm going to kick that off. What we're going to get back here is the object IDs that are a part of the response message after a successful write. Normally, these would go into a database for the application so that you'd know how to use them again. I'm actually going to stop it briefly so I can grab one of these OIDs and show you that we're actually putting data in there. If I go to our web browser, if I go to the IP address of the accessor and then the vault that we're using for this is called demo, I can simply append the object ID and make a web request and pull back this turtle picture. This is essentially what we've been uploading over and over again. So I'm going to kick this part off again, and we'll continually see the object IDs go by. At the same time that that's going on, we'll go over here and start the upgrade. So I'm just going to say upgrade the entire storage pool. You'll see over here that all of them got put into the queue and that they're all in a status that means they're requiring. You'll also notice that we just stopped the first one, and in this case, we're going to upgrade one slice store at a time based on this upgrade throttle that's right here. I'll go back into the upgrade throttle in a second. I just want to jump over here and show that we have one slice store down and we're still doing I/O operations without a problem. So we'll talk a little bit about why this upgrade throttle is 1. This is a relatively small system for us. It's only a 9-wide system. So there's only so many different ways to still have a decent IDA or threshold configuration and still have good reliability. So if we go look at the vault and how it's configured, I'll go over here. You'll see in this case that it's a 9-wide by looking at that part there, and that it has a threshold or a read threshold of 5. So that means that 5 of the 9 have to be up at all times. We also have a concept of a write threshold, and that means that you have to have that many devices up for a write to be considered successful or in theory, or the other way to look at it is we have to finish at least 7 of the writes before we'll send an acknowledgement back that the write has finished successfully, and we'll still try to write the other 2 after the fact. And then there's the alert level, which is essentially generating this yellow alert for the vault, but it also controls how many devices are upgraded at a given time, hence the upgrade throttle of 1. In a larger system, like say you had a 36 wide system, you may have an alert level set at like 32, so you could do 4 slice stores at a time to make the upgrade go a little bit faster. Is there any questions on that kind of part of the conversation?
Looks like we're good.
Okay, we'll go back over here and just show that we're still churning away here, and we'll go back to the maintenance tab and see how far we've gotten on the first slice store. So it's currently rebooting. So it has gone through, downloaded the upgrade files from the manager that it needed, applied those, and now as a part of the upgrade process, it reboots. It's going to continue running, so we'll let that continue, and we'll go look at some other stuff while it's going ahead. So we'll go look at some of the graphs and some of the other kind of information that's in the manager. So we'll go look at an accessor, for example. We'll see what kind of data. The system isn't extremely busy, so we'll see if we can find some meaningful data to look at. So there's a couple different graphs that are kind of helpful that we have as part of the system, and they're available for any appliance that's in the system at this point. We can get device load and CPU type usage information. As you can see, these systems aren't extremely busy based on the limited workflow we have on them. We'll go look at the network graph. Here's another graph, for example, that in this case, we're only using each 0, but as you can see, we also have graphs for each one if we decided to bond them. We'll go look at a larger version of this graph. It's a little bit probably easier to see for you guys. Currently, we're only looking at the last 24 hours, and you can see kind of the spikes here of very limited use on the system since it was sitting dormant for this demo. In some cases, you may have quite a few things down here, and you can actually turn off lines and turn them back on. This is all based off of Google Plot.
Yeah, you can easily have graphs that have 50 or 100 different lines on them, and then you're able to select which lines you want to see on the graph to kind of separate the signal that you're interested in out of the rest of the noise.
You want to see all 50 at one time?
If you're really smart, you can look at all 50 at one time.
So, and obviously here you can change the time frames and things of that nature to look at. So pretty much all the graphs have obviously the data that they're representing is different, but the look is pretty much what we're looking at right now, the look and feel. So that's for those graphs. The other one that we can look at is vault specific. Instead of looking at, we won't go look at a slice store, we'll go to the vault layer. And this is probably one of the more useful ones in the vault. It's good to be able to look at this over time and see kind of how much space you're using, of raw space that you're using and kind of how it's going up over time. As you can see, we did some initial writing, and then we didn't do any writing for several hours, and now we're doing a little bit more now. The other thing you can see is, on the graphs, if you pick a data point, it will actually come up and give you the actual data point itself in the little hover window. The other thing that you can see from the vault level, and this is kind of a good example of one that's got a few more lines on it, not crazy, but a few more, is as a part of our effort to make everything bit perfect, we do scan through the system as a background task to identify slices that are missing from a single slice store due to a disk being bad or replaced, or maybe it was offline for a period of time. We scan through the system, and this is the activity in the graph that is being represented, is how fast are we scanning through the system on each individual node in order to figure out if we have any pieces to fix or not. So we call it rebuilding, and there's really 2 components to it. There's a scanning part, which we're looking at the graph now, and then below it, actually, let me get to the right window. Below it, we have a rebuilder graph as well. And in this case, the rebuilder is loading now on the bigger window, really won't have much data in it due to the fact that nothing's really been down or replaced on the system. And it's being really slow, so we'll just look at it in the smaller. As you can see, there's nothing really down here. So let me go back to the upgrade again. So we're still writing. And if we look here, Slice Store 1 is complete and is verified. And you can see it's green again. And now we're currently rebooting the second one. And we're still writing data like nothing has changed. Just going to wait a second, Rob, to let the status update. Since we're on a screen, it should update probably in 30 seconds or so. I don't know if you have anything you want to say while we're waiting on that.
Well, just ask the audience, were you guys able to follow what was going on here? The idea was to, start this script that's just kind of writing many different copies of that turtle picture, storing them, each as different objects within each object IDs. So that window that had all those numbers, those were all the object IDs that were coming back for each of those operations. And that was continuing without interruption while we started this upgrade process and started, in this particular case, upgrading Slice Store nodes one at a time. So
do you see how we are not verifying, Rob?
I do. Yep. So right here, this one's just about done. It says it's verifying, and then it will start the next one. So.
I mean, in the case where you took a node down, a slice store down, and presumably one of the slices actually does belong on that node. So how do you go back and fix that node back up to?
Yeah, so that's an excellent question. So so you took one slice store down. We're still storing pictures. So what's happening to the slices that should be going to that node? They're clearly not going there. So when it comes back online, the scanning process that Mike talked about will identify that a slice is missing. We also have a separate data integrity process. Every time we read a slice of data, we do an integrity check. So if there's a URE and the data is corrupt, we'll be able to flag that slice as being bad and we'll know not to use it. There's a process that runs on the Slice Store node in a distributed way called the rebuilder process that will replace any missing or corrupt slices with a good slice. So via the rebuilder process, those slices that weren't written to Slice Store 3, because right now it's in the process of being upgraded, will eventually be rebuilt and will appear on Slice Store 3, and will end up with a full width of 9 slices on 9 different.
In order to do that, does it have to
stores.
read the other slices from all the other?
Yeah, exactly.
Calculating some sort of parity or something like that?
Yeah, so it reads a threshold number of slices from other slice stores so that it can recreate the object and then recreate the slice that it needs to put in place. And many slice stores in the network will participate in that process. It's not like one slice store has to rebuild its own data. So if you had a large chunk of data that was missing because a drive, catastrophically failed and took all the data with it, then every slice store in your dsNet will help rebuild that data so that it can be done more quickly.
It's also rebalancing, right?
It is also rebalancing, yes. Yeah, it's also rebalancing across the slice stores as well as across the disks in an individual
I kind of
slice
already
store.
asked for, is it location aware, but even if it was only in one data center, could you make it rack aware?
Yes, you can make it rack aware.
If I lose an entire rack, I will lose half of my, well, I want to lose only half of my slices and have failover capabilities and not having 80% of my slices in one rack.
Correct.
Is that a possibility?
Well, so making sure that your slices aren't overly concentrated in one rack has mostly to do with how you physically distribute your dsNet servers across the racks that you have available.
If I say I want to have 10 slices out of 20, this would be good, but how do I distribute that evenly in 2 racks?
So might be easier for me to explain an example with more racks. If you had 3 racks, then you would use all those slice stores in a single storage pool. It'd be one width of slice stores. So if you lost a rack, you would lose a third of your slice stores.
Yes.
And your erasure coding setup, your width and your threshold, would be configured so that you could lose a third. Probably be set up so you could lose a third plus
Yeah, but
one
I want
or
to
two
know
more.
that it's only a third in that rack. If it's not rack aware, I could have 70% of the slices in one rack.
The software.
Avoid that or not.
The software, the software is not deciding which slice store to use based on which rack the slice store is in. So in that sense, it is not rack aware. From a serviceability point of view, when you set the system up, you can attach information that tells you which slice stores are in which rack. So when one fails, it's easier for you to find it, which is not really related to your question, but I'll just throw that in while we're talking about it. But typically the way our customers deal with this issue is if they have enough slice stores, they spread them out across a number of racks so that no rack has more slice stores than they can afford to lose.
But the system is location aware, so if slices are in different, like 2 slices per location or something like that, it'll try to spread the data for the data vault.
It's really when you configure your system, think of your slice stores as an array of nodes. All right, so if you only had 9 slice stores, you got 9 slice stores, and so each one's going to have 1/9 of the slices. If you had 18 slice stores, you basically have, in a 9-wide system, half the objects will be sliced onto the first 9, and half the objects will be sliced onto the second 9. So in that case, if you lose 2 slice stores in the same rack, you aren't losing ever 2 slice stores that have slices of the same data, if that makes sense. So that's how you configure your system or deploy it to get the maximum tolerance of that's possible.
But the location awareness is really on the read and stuff like that. So you're detecting how quickly the slices are coming back, and then you're going to be using that preferentially again the next time.
Yeah, when it comes to where slices land, that's all really done logically in the namespace. So that process is not physically aware of location. Did I at least clearly answer your question?
Yeah. I mean, I don't ask you to have every single failure covered.
Yeah.
Losing an entire rack is a pretty big issue.
Well,
I mean, you have bigger issues if you lose an entire rack.
Right. Well, imagine you had only 1 rack worth of slice stores and you lost that rack. There would be nothing you could do. If you only had 2 racks, it's just as bad. If you have 3 racks worth of slice stores, or you're willing to spread your slice stores into 3 different racks, then you can build a system that can tolerate a rack failure with no problem. And it's not because the software is location aware, it's just because you distribute the slice stores across different racks in the same way that you would distribute them across different physical sites to get physical site failure tolerance. It's probably a better way to explain it. All right, so now you can see we're up to slice store number 4. Anything else that you wanted to highlight or add, Mike?
No, I think it's easier for you to have that part of the conversation. It's hard for me to hear that. So.
All right, well, thank you very much. Any other questions about the demonstration? Or about this example of internal storage as a service use case? The reason we showed this here is because for this type of an application in particular, where this customer is supporting multiple different services to multiple different internal customers off the same storage system, how would they ever find a window that they could take the storage down?
So this is great for the slice stores, but the accessor stores, I mean, are they done in the same fashion? Is this writing activity going to be spread across accessors?
Yep, writing is spread across accessors, and so there's no requirement that a particular write goes through a particular accessor. You can take an accessor out of your accessor pool, and it doesn't disturb anything. Customers that have large numbers of accessors often put a load balancer of some sort and use that to make sure that the traffic gets equally distributed across the accessors. But the accessors are stateless devices, so they don't, no one accessor is special relative to any other accessor.
And their purpose is to split the data and provide erasure coding, is that?
Correct. Yep. They provide the interface, they receive the data, they create the slices and store the slices to the slice stores, or on a read, they collect the slices they need, reconstitute the object, and return it to the application. All right. Very good. Well, Mike, can you make me the presenter once again, please?
I think I can.
We'll hope you can. I am now the presenter. Thank you very much, Mike. Thanks for your help with the demo.
Yeah, no problem. Thanks, guys.